So I think where we finished on Friday was not quite at the end of the logic of adding angular momenta. Remember, we had these two gyros in a box. The rate at which one span was J1, the rate at which the other was spinning was J2. And we were trying to understand what the states of the box were, which had well-defined angular momentum, and what predictions we would get for if we opened the box and measured the individual gyros. And we had shown that what you would expect on physical grounds was the case, that if you orient the first gyro with the z-axis and the second gyro both with the z-axis also, then the two angular momenta would add, because as if they were parallel to each other, and we would get a state with total angular momentum J1 plus J2, and apparently all of it down the z-axis. And then we used the J minus operator, the reorientation operator, J minus, to create this state in which we still had the same large amount of angular momentum because the two gyros are parallel to each other. But we didn't have it all parallel to the z-axis. And the algebra led us to this expression here, that this state is a linear combination of the state in which the first gyro is offset from the z-axis, but the second gyro is on the axis, and the state in which the first gyro is on axis and the second is offset from axis. And I was just saying, as the lecture closed, how to get this object here. This object here has to be a linear combination of these same two states. So this is a state of the box. This is a state of the box. Neither of these states of the box is a state of well-defined angular momentum of the box. This linear combination is, and there's another linear combination of these two, which is a state of well-defined angular momentum. That's this state, which has less total angular momentum of the box, and it has this state that we're looking for has to be orthogonal to that. And one good way of writing it is to say that J minus 1, so this is the state in which the gyros are not parallel to each other quite, but all of the angular momentum available, given that they're not parallel, is along the z-axis, that this is the linear combination orthogonal, which you could write as J2 over J of J1, J1 minus 1, J2 minus root J1 over J of J1, J2 minus 1. So here we have the slightly strange thing. We have the state in which, so this is a state in which the two gyros are not quite parallel to each other, which is why the total angular momentum of the box is less than maximum. Here they are parallel to each other, and yet when you look in here, it turns out it looks as if they're not, because one of them is aligned with the z-axis and the other isn't. And here we have a linear combination of the same two states of the contents of the box, but with different coefficients out front, and crucially a minus sign here, and that has the physical interpretation of the two gyros not being parallel to each other. So let's try and clarify this strange situation. Well, get used to it, I suppose, is the state of affairs, by doing a concrete example. What does it look like in the very important case that we say J1 is 1 and J2 is a half? That means, obviously, that J, the maximum angular momentum we can get, is 3 halves. And we're going to have a diagram now that looks like this. So that was all in general. Now we're going to be looking more, we can say more concretely what we're going to have. We're going to have 3 halves at the top here, which is going to be the same as 1, well, we can just say 1 and plus. So you're using a shorthand notation here, right? So I've got that J1M is now going to be objects like 1, nothing, and minus 1, right? Because there's no need to write this down. I'm writing down the possible values for m. M is 1, m is nothing, m is minus 1. And J2m can be, because J2 is a half, I can write this as plus and minus, where I'm writing down the values of m in the sense of plus a half and minus a half, right? That's a shorthand notation that makes life a bit easier. So this is just a different notation for that state, a more compact notation for that state. If we would come down here, what would we have? We would have 3 halves, 1 half, right? That's because J is 3 halves. And what would it be? It would be the square root of 1 over 2. Sorry, not at all true. It would be J1, which is 1, over J, which is 3 halves. Oops, I'm in danger of running out of space. Let's just shave that off. It'll be 1 over 3 halves times nothing plus, and now I want this state, which is going to be a half over 3 halves, the square root of a half over 3 halves of 1 and minus. So what does that, let's just clean that up a little bit. That's equal to root 2/3 of nothing plus, this is going to be 1/3, root 1/3 of 1 minus. Notice a nice thing about this is that the linear combination of these states of what's in the box that we generate comes out beautifully normalized. This thing squared plus this thing squared, 2/3 plus a third comes to 1. It comes out normalized automatically, and that provides a nice check on your algebra. So it's good to check that it is properly normalized, because if it isn't, the algebra's gone wrong somewhere. We now have a physical prediction. If you look at this state here, and what we might be talking about now, that J1 equals 1, that might be the orbital angular momentum of an electron, and that J2 equals a half might be the spin angular momentum of the electron. So we might be talking about the total angular momentum of the electron due to both its spin and its orbital motion. And if you would look inside the box, if you would examine the atom, the electron in detail, when it was in this state, you would find that there was a probability of this thing squared, i.e. 2/3, that the orbital angular momentum in the z direction would be nothing, and the spin would be along the z direction, and there would be a probability of 1/3 that the orbital angular momentum would be all parallel to the z-axis, or as parallel to the z-axis as it can be, and the spin and the electron spin would be pointing downwards. All right? So that's the physical interpretation of this. So we have that P spin up equals 2/3, and P spin down in this particular state is equal to 1/3. That's the physical meaning of these numbers here. If we would, okay, so now let's ask, what's this state here? We would like to, there are some more states to find. This is the state in which we have we have 1 unit less of angular momentum than we have on the outer circle. So this is the state, a half of the box. It's going to be a linear combination of these two things, and it's going to be the linear combination which is orthogonal to these two things because it's an eigenket of the total angular momentum squared operator for the box, which it's an eigenket of that which has eigenvalue different from this. So it must be orthogonal to this by the orthogonality of the eigenkets of Hermitian operators. And what is it going to be? It's going to be root 1/3 of this, nothing plus, minus 1/3, root 2/3 of 1 minus. So now, in this state, the odds, when you look in the box, of what you find are changed. In this state, which has less angular momentum in total, the probability of spin up is this thing squared, i.e. a third, and the probability of spin down is 2/3. So that's the physical implication of this. It's an interesting exercise to apply the J minus operator here to generate this. So if we take this state and apply the J minus operator to it, on the left side we're going to get 3/2 minus 1/2, which is this state here. Let's just have a new diagram because we're running out of space there. So here we have 3/2 minus 1/2. And it's going to be obtained by using the J minus operators on the left and the right of that equation. And I recommend that you do this. I'll just write down what the answer is for the moment. It's going to be 1 over, well, it's actually obvious, 1 over 3 of minus 1 of minus 1, sorry, plus 2, 3 square root of nothing minus. Now, it should be this because there should be symmetry between the plus, this state down here, physically, sorry, let's write it in here. This state here, physically, it's evident that this has to be, this is obviously minus 3, this is 3/2, and all of it anti-parallel to the axis, 3/2 minus 3/2, and physically, it has to be that both of them are pointing down, right? So it has to be minus 1 minus orbital angular momentum down, spin down, which is obviously the sort of negative of what we put at the top there. This thing, similarly, has to be, physically, it should be that you can get this thing by changing 1 to minus 1 above, minus to plus, naught stays alone, and plus to minus. And indeed it does, right? So it's an exercise that I recommend that you check that when you use J minus to go from here, you do indeed arrive here, which is where you expect to arrive by the symmetry between plus and minus. And you do. So what's happening here physically? Let's see if we can form some kind of physical picture. We can only do this to a limited extent because of the big role that quantum uncertainty plays with small spins. But the physical idea here is that, so let's take this 3/2 1/2 state. What do we have? We have some angular momentum vector which is in some sense 3/2 long, and it's only got 1/2 of it in the z direction. And that is some superposition of the angular momentum being, the orbital angular momentum being more or less in the xy plane, and the spin carrying you up. So you add this vector to this vector, you get this vector. That's sort of what the first term up at the root 2/3 of naught plus symbolically indicates, spiritually indicates. We then also have another linear combination which is 1 over root 3 of 1 minus. Now, how do we understand that? Well, we have to draw a diagram that's something like this. So we're now combining the orbital angular momentum, which is sort of vaguely along the z-axis. Remember, I stressed that when you're dealing with small spin systems, you can never get the angular momentum exactly parallel to the z-axis. There's always a significant amount in the xy plane, right? So this is the direction of z. This is the xy plane. So this vector shouldn't be going straight up, and I shouldn't have drawn this vector going straight up really either. That should have been at some funny angle. In fact, let's improve the quality of the diagram a bit by making it not go straight up. Let's make it go like that. And then I've got minus pointing down, but again, it's not pointing straight down because there's always, I stressed, with spin a half, there's as much angular momentum parallel to each axis at all times. So this is the sort of diagrammatic representation of that expression up there. And how do you think about this? A possible way of thinking about this physically is to say to yourself, well, the angular momenta of the orbital and the spin angular momenta are interacting with each other, and as a result of it, precessing around this fixed vector. This is the total angular momentum of the box, which by conservation of angular momentum must be a fixed thing. So you can imagine that these two vectors are precessing around this vector here, and here we see two snapshots of possible configurations. Right? So if you imagine this thing moving around like that, now we see this, sometime later we see this, and then it'll precess back to that. Now that is not really, strictly speaking, a legitimate proceeding, because in doing all this stuff, we never said anything what the Hamiltonian was. We never said anything about that. We just had these two gyros in a box, and they weren't physically interacting in any way. Consequently, they have no means mechanically for exchanging angular momentum. And yet, when the box is in a state of well-defined angular momentum, we have these results up here, and we have this state of the box is a superposition of these states of the contents of the box. So beware of this picture, but there is a certain amount of intuitive satisfaction in this picture, and it does at least give you a physical understanding of why it is that a state of well-defined angular momentum for the box is not a state of well-defined angular momentum of the contents of the box. Because already classically that would be the case. And what's happened is, by insisting that the box has a well-defined angular momentum, we have forced the particles to be correlated, because if the angular momentum of the orbital angular momentum, or the first gyro, is doing this, in order that the total angular momentum is this, the other thing has to do that. So we have forced a correlation between the two gyros, or between the spin and the orbital angular momentum, and that correlation is reflected in the entanglement of these particles in the sense that we discussed when we talked about composite systems. Okay. And in real physical circumstances, like an electron, if we do have an orbital angular momentum and spin angular momentum, then there is a physical coupling between the two provided by the electromagnetic field, and it is then legitimate to think about these things as precessing around. The other thing that I should probably say is that this diagram doesn't really work. You won't, if you try and make this diagram work with proper lengths, you give a proper length to this, and this thing should equal this thing, and this thing should equal this thing, you won't be able to make it happen, right? And the reason you won't be able to make it happen is because this is showing something in only 2 dimensions, and what's really happening is in 3 dimensions. So you've got to imagine, so we don't know anything about what's happening in the xy plane. Those were the terms. That was the deal we did. We said we were going to have eigenfunctions of L squared or J squared and Jz, and having chosen to know something about what Jz is doing, we've given up on, we've surrendered knowledge of what Jx and Jy are doing. So what's happening in the plane perpendicular, this is the xy plane, right? It's not x and it's not y, it's just things happening in that plane, means that you can't really draw this as a 2-dimensional diagram. So that's why you can't make it work vectorially. Well, I think we should leave the addition of angular momenta and turn to our final topic, very important one, which is hydrogen. So obviously atoms are terribly important. We're made of them. That's most of what we see here and elsewhere. And they're also have played a crucial role in the development of quantum mechanics. Quantum mechanics was developed in order to build models of atoms. It is amazing that this enterprise was successful, because even simple atoms, like an oxygen atom, is substantially more is a substantially less friendly dynamical system than, say, the solar system, because it contains, right, an oxygen atom contains 8 electrons and the nucleus. So it's sort of the same order of the number of particles as the solar system, but it is much more horrible dynamical problem than the solar system because the electrons attract each other much more strongly than the planets attract each other. So the approximation, which is fundamental to understanding the solar system, that the planets move around in the gravitational potential of the sun, and we can neglect the gravitational potential of the other planets while we do that and make ourselves a model, and then add in as a perturbation the action of Jupiter. The forces between the planets are not negligible. They play a crucial role in structuring the solar system, but you add them in later, and they're a very small approximation relative, very small matter relative to the electric attractions of the electrons, which are really jolly large. Another problem about an oxygen atom is that the particles are moving with speed v, which is on the order of it's on the order of 8 over 137, so several percent of the speed of light. You're talking about a system which is mildly relativistic. The contribution of relativity to motion in the solar system is very much smaller. We're moving at 30 kilometers a second, which is less than 1,000th of the speed of light. So relativistic corrections are much more important. Another very serious problem is that these particles which are moving around in an oxygen atom are all magnetized gyroscopes, right? They all have spin, significant amount of spin. Of course, the Earth has spin, but it spins very small. It's enormously small compared to its orbital angular momentum. And the Earth is magnetized, but the magnetic couplings between the sun and planets and between planet and planet are completely derisory and negligible. And yet it took physicists, to get a pretty good understanding of the solar system was the work of the whole 18th and 19th centuries. It was with the work of Bessel that the classical structure of the solar system was pretty much under control. But as Poincaré, who lived at the beginning of the 20th century, pointed out, there was still an enormous gap and problem about the long-term life of the solar system, and the long-term life of the solar system is still an active topic of discussion, and it turns out to be a very interesting and finely balanced problem. So even though an oxygen atom is very much more complicated and unfriendly a dynamical system than the solar system, actually it's very much better under control. Quantum mechanics enables you to bring it under very much better control than even today we have brought the solar system. So it's an interesting point that these systems are, in quantum mechanics, actually rather easier to do than the corresponding classical system. But they're nonetheless very complicated, and we have to proceed by stages. And what we're going to do is study, well, hydrogen, of course, is very important. It's a tremendously important atom, but we're also going to use it as a building block for understanding atoms in general. So we're going to talk about, so what are we going to do? We're going to talk about the gross structure, what's called the gross structure, of hydrogen, hydrogen-like ion. So what do I mean by this? Gross structure. This means that we are going to have no relativity, no spin. Intimately related to relativity, in fact. We're going to have, so we're going to be left with point spinless particles which interact electrostatics, right? In non-relativistic mechanics. And over here, what are we going to do? We're going to say that the nucleus, the charge on the nucleus, is going to be Z times the electron charge. So we're putting in here a number which in hydrogen will be 1, but which we can make larger in order that we can discuss the motion of electrons around oxygen nuclei or other nuclei as a building block. No spin. Oh, yeah. No, electrostatics, in other words, no magnetism. And the key thing really is we're leaving out relativity because magnetism is a relativistic correction to electrostatics, and spin arises naturally when you think about electrons in the context of relativity, as I hope you'll appreciate next year. So we're leaving out effects which are actually quite important, but one has to proceed in steps. So now what we're going to do, what we're obviously trying to do, is we're trying to find the stationary states of an atom, of a system, which consists of one electron, one nucleus with that charge. So we want the stationary states because they provide the key to the dynamics, usual situation. So what's the Hamiltonian under these approximations? Well, it's going to be the nuclear kinetic energy, the kinetic energy of the nucleus, p nucleus squared over the mass of the nucleus, twice the mass of the nucleus, plus the electrons' kinetic energy, plus the interaction energy between these two, which is going to be Ze squared over 4 pi epsilon naught xe minus xn modulus, right? So this is the sum of the energies, of three distinct contributions to the energy: kinetic, potential. Right, so we want to know what does this look like in the position representation. Right, we're going to we want to examine that equation concretely, and the way to go is to put this into the position representation. So that's to say we bra through by xe xn h and then what we want is the position representation of this, which is going to be minus h bar squared del squared with respect to xn over 2m nucleus, right? Because this is the kinetic energy operator, which we know that p is minus ih bar gradient, so p squared is minus h bar squared nabla squared. So what does this mean? This sub xn means this involves derivatives with respect to the components of the position of the nucleus. Minus h bar squared over 2 mass of the electron, del squared x electron, minus ze squared over 4 pi epsilon naught. This is already in the position representation, if you like, xe minus xn. So all this stuff times psi, I've run out of space to put it in, times psi is going to equal E times psi, right? So this is the usual stuff that psi, which is a function of x, E, and xn, so it's a function of 6 variables, is xn, xe, E. It's the wave function of the stationary state of energy E. So we've got here now, so we've reduced our abstract equation to a very frightening partial differential equation in 6 independent variables, right? Because we've got the positions, the 3 components of xn and the 3 components of xe. So it's we've got a PDE in 6 independent variables. The astonishing thing is that we can solve this exactly and without a huge amount of sweat. And as in the solution of any number of problems in physics, the key is to choose your coordinates correctly. That's quite generally the case, that a problem which is very frightening in general, with a clever choice of coordinates, you're all done. So we need new coordinates. We need to transform this equation to new coordinates, and the ones we take are big X, which is the center of, is classically the center of mass coordinate. So that's going to be me xe plus mass of the nucleus times the position of the nucleus over me plus mn. All right, so that's the center of mass coordinate. You may say, what authority have I got to use that in the context of quantum mechanics? And the answer is, strictly speaking, I made absolutely no claims as to the physical interpretation of this. It's just a suggestion of something we might use to simplify the algebra. But as rational beings, we know physically what that means. And then we'll have another, so that's 3 new variables, okay? Because it has 3 components, which are linear combinations of our old variables. And we're going to have another linear combination, and surprise, surprise, it's going to be xe minus xn, the separation. So all we do now is plotting mathematics in order to rip out of that differential equation xn and xe and insert the corresponding things with this. So let's see how this goes. Let's do d by dxe, right? Because that nabla squared e is sort of this operator dotted into itself. So let's see what is this? Well, the chain rule says that it's d by dx plus d by dr So this is the chain rule. Mathematics, nothing to do with physics, but because it's mathematics, it's definitely true. And this dot implies a summation, right? Because this thing's got 3 components, so this is dx1 by dxe, d by dx1 plus dx2 by dxe, d by dx2, etc., etc., etc. Now, fortunately, these partial derivatives are nice, friendly things because we just have linear combinations here. So I think we can easily see what this amounts to. This is going to be me of me plus mn. That's what this partial derivative comes to from up there of d by dx plus, and what's this partial derivative is nice and simple. It's just 1, so we're just going to get plus d by dr. So I've still got, this is a shorthand for 3 equations because this is d by dxe1 is equal to this thing times d by dx1 plus d by dr1, etc. We want this thing dotted into itself. So what we have to do is multiply this on itself with a dot between the 2. And what do we get? We get that del squared x sub e is equal to, we get this thing squared, of course, so we have me over me plus mn squared d2 by dx squared. Well, no, we can write that more handily as del squared with a big X, I think more clearly. And then we get this thing squared plus del squared with respect to del squared, where we're talking about the components. Here's the usual expression for del squared, but using the components of big X. Here's the usual expression for del squared, but using the components of the separation vector r. And then, irritatingly, we get a mixed term because we get this, because we're taking this operator and we're multiplying it on itself. So we get a mixed term of this operator multiplying the d by dr in the next bracket. And then we have this thing doing this. So we end up with plus 2 of me over me plus mn of d2 by dx dr. So this is not very nice. Nobody wants this. This is excellent. We've got a relationship. We've found a relationship for this, which we want, in terms of this and this, which are fine, but this is definitely not required. Would kindly go away. And we can make it go away easily by just working out what d by dxn is. That's going to be d big X by dxn, which is going to be mass n, mass of the nucleus over mass of electron plus mass of the nucleus, d by d big X. And then it's going to be dr by dxn, which is going to give us a -1 instead of a +1. So this will be minus d by dr now. And when we square this up to work out what del squared of xn is, we get this thing squared, of course, mn over me plus mn squared del squared, whoops, of big X. So that's this one squared. And then, of course, we get this one squared, and never mind the minus sign because we're squaring up. So this becomes a plus del squared with respect to the separation variable components. And then we get this on this, where now the minus sign is manifest. We get minus twice this, which is mn over me plus mn of d2 by dx dr. So we have expressions which are very similar, but include one has a plus sign, one has a minus sign. So what we want to do now is work out 1 over me del squared with xe plus 1 over mn of del squared with respect to xn. So 1 over me times that top equation plus 1 over mn times this, which is actually exactly what occurs in our Hamiltonian. If you go right up there, mercifully what we want is, in fact, the individual del squareds weighted by 1 over the mass. And what's this equal to? This is equal to, we get del squared x twice, once from here and once from there. We used to have an me squared over me plus mn squared, but we divided through by me, so we have an me. And then similarly from here we have an mn over me plus mn squared. That's the result of adding this with this weight to that. Similarly, what do we get here? We get a common factor of del squared r, and we have a 1 over me plus a 1 over mn. And these terms go away, right? Because by the time we divide it through by me, at the top, we have just 2 over me plus mn times that mixed derivative. And by the time we divide it by mn, we just have minus 2 over that, so they go away. So this that we want in the Hamiltonian is equal to this, which can be simplified and written as 1 over me plus mn del squared x plus 1 over mu del squared of r, where mu is exactly equal to me mn over me plus mn and goes by the name of the reduced mass. And you may already have met it in classical mechanics. I hope you have, but if you haven't, never mind. So we can now write our Hamiltonian, and I'll do it over here, I think, so we can keep in view the Hamiltonian at the top there. What do we have? We have that the Hamiltonian involves that, what we have is a minus h bar squared over 2, right. So that's going to give us a minus h bar squared over 2 mn plus me, or me plus mn I've been writing, del squared with respect to big X. We will have minus h bar squared over 2 mu of del squared with respect to the separation vector. Because this is the magic combination. Minus h bar squared over 2 times this is what appears in the Hamiltonian. So we get minus h bar squared over 2 times this, which is what I hope I've written down. And then we have to add in the potential energy term, which is a minus z e squared over 4 pi epsilon naught times the separation variable, where this is, if you understand me, the modulus of the separation variable. So that's what, in the position representation, with these new coordinates, our Hamiltonian is looking like this. And this is really beautiful because we can define this to be hk, and we define the rest of it to be h sub r. And what do we have? We have that h sub k commutes with h sub r. Why? It commutes because this is a function only of the x variables, the big X variables, right? It just involves derivatives with respect to big X. And those derivatives, these partial derivatives with respect to big X components, are with all the other coordinates held constant. And the other coordinates means the other components of big X and all the components of little r, because we made a legitimate change of coordinates. So this obviously commutes with this, because partial derivatives always do, and this commutes with this, because this is being held constant while we're doing these partial derivatives. So h sub k commutes with h sub r. Correspondingly, h sub k commutes with the Hamiltonian, and also h sub r commutes with the Hamiltonian. That follows immediately from the first thing, because obviously, this thing is hk plus hr, hk obviously commutes with itself, every operator commutes with itself, and we've established it commutes with r. So this vanishes, and similarly, this vanishes for the same argumentation. So we have three mutually commuting operators. That means there's a complete set of mutual eigenstates of h, hk, and hr. So we want eigenstates of this. That's what we set out to find. And what we've discovered is that if we find the eigenstates of this and this, all we need to do is multiply them together, and we will have eigenstates of this. So what does this imply? This implies that E is equal to some state of K times some state ER, or E sub K. Now, I have to be a little bit careful. I think I've said something that's not strictly speaking true. What we know is that there is a complete set of eigenkets of this, which are simultaneously eigenkets of this and this. It does not follow, and indeed is not true, that every eigenstate of this is simultaneously an eigenstate of this and this. There are eigenstates of this which are not eigenstates of this and this. But we will get a complete set of eigenstates of this, that's good enough for us, which are simultaneous eigenstates of this and this. So we've reduced the problem of finding the eigenstates of this to the subproblems of finding the eigenstates of this and the eigenstates of this. So hk is just the kinetic energy the kinetic energy operator of a free particle. Physically, it just describes the kinetic energy of the whole atom. The whole atom can cruise across your laboratory. It has kinetic energy. Are we interested in this? No. It's bloody obvious that the energy of an atom depends on how fast it's moving. We can deal with that. We've already studied we already last term studied the stationary states and the spectrum and everything else of free particles. We know all about it. Boring. Finish. So all we have to do is hammer away at this thing. What we want to know is, this is basically trivial and of no interest. So we focus in on HR. Now, we went to some considerable trouble to show, so this has to be studied. What we want to deal with is HR, ER is equal to ER, ER. And this is going to describe the internal energy of the atom, as distinct from the translational kinetic energy that it has, because it's moving. And we've been to some trouble to show del squared was equal to PR squared minus H over H bar squared. We showed a relationship between between del squared and what we identified to be the radial momentum here squared, and the orbital angular momentum operator, right? So this is right, basically we showed that L squared was R squared times the angular parts that we were familiar with inside del squared, the Laplacian. So this is the total orbital angular momentum. Total orbital angular momentum operator. And PR, let me write it down for you. PR, we figured out what it had to be. It turned out to be minus IH bar of d by dr plus 1 over r. That's what it looked like in the position representation, and it's the radial momentum operator. So let's just say what we've got. Let's write down HR now using this information. HR is minus h bar squared over 2 mu times nabla squared, okay? So what's that? That's equal to PR squared over 2 mu plus L squared, h bar squared, L squared over 2 mu r squared, and then minus z e squared over 4 pi epsilon naught r. That's so we've homed in on this operator. Our problem is solved once we find the eigenstates of this operator and the eigenenergies of this operator. And this is what it looks like. It involves radial momentum, radial position, radius. And for the rest, it involves the total orbital angular momentum operator. So the brilliant thing is that HR L squared equals naught. It's also true that HR comma LZ equals naught. Why is that? Because L squared, remember, it can be represented as a partial differential operator in terms of dB thetas and dB phis. So it clearly commutes with this, and it commutes with this, and it jolly well commutes with itself. Similarly, LZ turned out to be minus IH bar d by d phi, the azimuthal angle. So it commutes, and LZ we know commutes with L squared, and it clearly commutes with R and PR. So what do we learn from this? There's a complete set of mutual eigenstates of H and L squared. But we know all about the eigenstates of L squared. We've studied them ad nauseam, right? Which means that what we can do is we can say, it's legitimate to say, now it is not true that every eigenstate of H is an eigenstate of L squared. Curiously, anyway, it is not true that that's the case, but it is true that there's a complete set of states of the form E and L squared. There's a complete set of states E and L, which is such that L squared on EL, this is an eigenstate, that's what that's doing there, denoting that it's an eigenstate of this operator, and of course has eigenvalue LL plus 1, EL. So I've learnt that it is possible, it is legitimate to look for to restrict the search for eigenstates of this crucial internal energy Hamiltonian to states which are eigenstates of the total angular momentum operator. And as we'll see tomorrow, that then reduces the eigenvalue problem associated to HR to just a one-dimensional problem, very closely analogous to the simple harmonic oscillator, which we've already sorted. And it will yield to the same line of attack that we used on the simple harmonic oscillator, namely ladder operators.